Okay.
Okay, yes, seems it's working. Okay, good afternoon, everybody. We are glad to have you here in DSB 2021. The latest addition is that we are also we are actually streaming live on YouTube. And you can find for that the links on the DSB webpage. And that has been one of the reasons that we are slightly late for the opening, because as you know, it never works as you expect. Anyway, a few more instructions. We are using AirMeet, which is this new platform for virtual conferences. According to our tests, it looks like it is the one that is able to better help having interactions between the people. Anyway, we are experimenting with that, and so we are very careful. We're going to be very careful with your observations and with your requests for help, and we expect them to help. So if you have any questions, please write in the chat. For who is attending via YouTube, there is also the chat there. So if the people on YouTube, you have questions, write them in the chat, and then I will relay them to the speaker at the end of the talk. I want to thank all other organizers, starting from Yuri Pirola, that is here with me, Paola Bonizzoni, and Raffaella Rizzi, who all have been extremely helpful, and without them, I'm sure that we will not be able to have a successful workshop today. It is a pity that we are not able to have you all in Milan as we expected at the beginning and we hoped for, but well, it is clear that it's not possible. Hopefully, we will be able to organize DSB another time and to have you actually in Milan. We are going to start with the first talk in 8 minutes, 13:25. The schedule is that each talk is going to be 20 minutes for the talk and 5 minutes for the questions. What else? You will be able to move across tables to talk with different people once the talks are over. Anytime you go to a different table or you are in the lounge, your microphone will be muted automatically. So be aware of that. If you want to talk, you have to unmute yourself. Somebody has asked if the streams will be recorded and available on YouTube. We will have the video, and I think that afterwards, after the conferences, we will ask the authors if they are willing to have them publicly available or not, because there is also a privacy problem that we have to take into consideration. So we don't know right now, and we'll see what the authors of the single talks will decide. So I think I'm done with my presentation. We have 5 minutes before Sebastian Schmidt is going to introduce is going to start with this talk. Again, we hope that you are going to enjoy the conference and you are going to have a nice time today and tomorrow, and and we hope to see you in person shortly.
I don't know if Yuri wants to add something more.
Just a big thank you to everybody for being here. Also from me, and it's all. For any question, please contact me or Gianluca or the other organizers. We are here for that. So enjoy the conference then.
Okay, so maybe you can start inviting Sebastian Schmidt, and so that we can get ready for his talk.
Okay. Oh, I see that some of you are using the chat for question. Please during the talks use the tab questions on your right hand side, so we can collect them more easily and so on, instead of the chat, I mean.
Yes, so this applies for who is connected via the AirMeet. For YouTube, there is only the chat, and I will take care of them.
Sure. Yeah. Yes. Perfect. Thank you very much, everybody. Okay, I'm reading your question. Okay. So we take a very, very short break while we are inviting the first speaker to the stage. So many of you, it's so difficult to...
Hello.
Hello, hi, Sebastian.
Hi, Sebastian.
Oh.
So,
just a few minutes, just to be... If you want to prepare to share the screen, the meanwhile. Perfect.
okay, so I think that we can start. It is my pleasure to have Sebastian Schmidt here to start the DSB 2021 workshop with a talk titled Genome Assembly, Universal Theoretical Framework, Unifying and Generalizing the safe and complete algorithms. Thank you again, Sebastian. The stage is yours.
Thank you very much. It's also a pleasure for me to talk here today. So, first of all, the project you already heard. My co-authors on this project are Massimo Cairo, Shabazz Khan, Romeo Rizzi, Alexandro Tomescu, and Elia Cirondelli. And today, I will first of all give you a short introduction about genome assembly and safety in genome assembly, and then also motivate why we might want more, in practice, more intricate models of genome assembly. And then I will introduce to you the current safe and complete algorithms in genome assembly. These are only for rather simple models of genome assembly. Then I will introduce to you the hydrostructure, which is a theoretical construct that is able to aid us in all the more complicated models of genome assembly for the characterizations of safe solutions as well as the algorithms. And then I will introduce to you how the algorithms work a little bit. So first of all, genome assembly and safety. So in genome assembly, we usually have a genome graph that's used by almost all modern assemblers. And in this graph, each edge is part of the original genome, and the genome is a walk in the graph. And for example, if we know that the graph is built from a single circular genome, then in this graph, our original genome would be a single circular walk. On the other hand, if we would know that there are multiple circular genomes in our data, then we would have multiple circular walks that represent these genomes or chromosomes, for example. Now, you might notice a challenge here. It's not unique. What is the correct solution walk in this graph? So what do we do in practice about that? We find only safe subwalks of the true genome. These are those walks that are subwalks of each possible solution walk. So they are then definitely part of the original genome. And now that we only report subsolutions, we want to be as complete as possible because we want to report as large solutions as possible still. Okay, so much for the short introduction. Now let's come to the practical issues. So let's look at some genome, for example. I have here a genome from a diploid species. There's a copy from the father, a copy from the mother, and this one's linear. And here there's a single nucleotide polymorphism, SNP. Let's construct the genome graph of this genome. This is an edge-centric de Bruijn graph, and it would look like this. And I drew here as a blue line the genome, the copy of the mother, the chromosome of the mother. And now we've seen this graph, for example, over here. The structure here is called a bubble. It happens when there's, for example, a SNP in the data or just some error in the data that we would need to resolve now. And then also in practice, we often get some edges, I call these red here, where the coverage is low. And then it's not always clear to say if these are actually part of some of the genomes or if these are actually errors. And let's look at how a classical assembler would handle this kind of genome graph. So first of all, it would pop this bubble. It would get rid of all the low abundance edges along with their nodes. And then it would compute unit ticks on this graph. Unit ticks are paths where the inner nodes have in and out degree 1. So like this one here, for example. And as you can see, if we assemble the unit ticks of this graph, we get down here, I aligned the unit ticks to the genome. We get a fragmented and also assembly that also misses some parts. On the other hand, in this example, if we would now apply a more complete algorithm for a more realistic model. So in this model, we now assume that we make these red edges here not covering. That means they do not need to be covered by the solution walks. They just can be covered if the rest of the graph topology requires it somehow. And also here for this bubble now, instead of popping it, we keep it here, but we mark it as invisible. And then we can later on, this hides it from the safe solution walks from the context, but we can later on come back and resolve it with some other methods. And if we now compute the safe and complete solution of this genome graph, then we get these green context down here. You see there's less of them, they're less fragmented, and they also cover the whole genome much better. So this is the motivation for why we would want more complicated or more intricate models of genome assembly in practice. And let's quickly look at what currently exists in terms of safe and complete algorithms. So for the single circular model that we have seen in the beginning, there are omnitics. This is the characterization of the safe walks in this model. They were characterized in 2017, and there was an optimal order of MN algorithm that was published 2019, and then also an output optimal algorithm. This runs in size linear to the input, plus size linear, runtime linear to the size of the input, plus runtime linear in the size of the output. And this was published in 2020. And this is actually useful in practice because while in the worst case, the total length of all the omnitics is order of MN, in practice is usually much lower. And there's also an algorithm for the multi-circular model that runs in order of M squared N. And these algorithms are all based on theory of forbidden paths. What's a forbidden path? Well, if we look at this blue walk here, a forbidden path in this blue walk would be a path like the red path here that repeats an inner subwalk of the blue walk. And if such a path exists, then this blue walk would not be an omnitic. If no such path exists, then this blue walk would be an omnitic. Now, this is how these older characterizations work. Now we also want to, like as I motivated in the beginning, solve more advanced models. For example, if we know that we have two copies for each chromosome, we want to have maybe a fixed number of solution walks. We might want to model linear genomes. Most vertebrate species have linear genomes. And we, as I motivated in the beginning as well, we might also want to model that only a part of the graph needs to be covered, as well as we might want to make part of the graph invisible. And now we would not want to, again, go for each of these models, for each of the combinations, through the whole theory again. But instead, we would like to have one unified theory for all possible combinations of these models. And for this, we introduce the hydrostructure. The hydrostructure is defined on a walk W, and it's defined in a strongly connected graph. For not strongly connected graphs, we can use the hydrostructure in the strongly connected components, and then do something else in the edges between these strongly connected components. But the hydrostructure actually solves the part that's hard to solve. The part between these strongly connected components is simpler to solve. And for the purpose of this talk, I will restrict myself to W being, first of all, a path, so it doesn't repeat any nodes or edges. And then also, I want it to be a non-trivial hard. What is non-trivial hard? A non-trivial hard is a walk that starts with a join arc. Usually this is a join arc because there are two incoming arcs into this node here. And it ends with a split arc. This is a split arc because there are two outgoing arcs from this node here. So we only consider these kinds of walks. And now I will first of all describe the hydrostructure from a bit more abstract level. Then we will go into the definition. We will look at some important characteristic of the hydrostructure. And then I will explain to you how it is applied in practice. So first of all, the hydrostructure decomposes our graph into four regions: the cloud, the vapor, the sea, and the river. And there's a restricted connectivity between these regions. This is motivated a bit by the water cycle. This is where the naming comes from. So for example, from the cloud, water rains into rivers or dissipates into vapor. From the river, the water flows into the sea. From the sea, water evaporates and then collects afterwards as clouds again. This is how the connectivities work in the structure. And now in the structure, we have a very important property. That is, if this vapor here is a path, then our walk W is a C-cloud bottleneck. What does C-cloud bottleneck mean? C-cloud bottleneck means that whenever we go from C to cloud, we need to use the whole W as a subwalk. And this is now very useful for our safety problems, because now for any model of genome assembly, if we can prove that each solution walk in this graph goes from C to cloud at least once, then we have proven that our walk W is safe. On the other hand, if we have a counterexample, if there is some solution walk that does not go from C to cloud, then we have a counterexample, and then we know that W is not safe. Okay, so much for the abstract overview. Let us go into the definition. So I have again the walk W. I call the first edge F, the last edge G. And now we define two sets, R plus of W, R minus of W. R plus of W is everything reachable from F without using G. So it's this colored region down here, the vapor and the C. R minus of W is everything backwards reachable from G without using F. So it's this colored region up here, the cloud and the vapor. And now we define our four sets. The cloud is R minus without R plus, the C is R plus without R minus, the vapor is R plus, and R minus, the cut set, and the river is everything else. And now, just by this definition, we get our property that our W is a C-cloud bottleneck if and only if the vapor is a path. And since this property is so central, let's also look at the proof idea of this property. So I brought here again the definitions of R plus of W, the definition of R minus of W, and here a definition of the C-cloud bottleneck. So W is a C-cloud bottleneck if each walk from the C to cloud has W as a subwalk. And now we can look at our lemma. So the bottleneck property is that W is a C-cloud bottleneck if and only if the vapor is a path. And to prove this, we first of all notice that our arc F is the only way to enter R minus, because R minus searches backwards from G and only stops at F, searches in G without F. Symmetrically to that, our arc G is the only way to exit R plus, because in R plus we search forwards from F and we only stop if we reach G. And this gives us a nice subproperty, that is that each walk from C to cloud, when it needs to first of all enter R minus at some point, it needs to exit R plus at some point, and therefore it needs to use F and then G. Therefore it also uses the head of F and the tail of G. So it has some head of F, tail of G subwalk that we call X now. And if we now take a minimal one, then we know that this one is in the vapor, because then it doesn't repeat the head of F or the tail of G, and our walk W here is always in the vapor. Now we can assume that W is a C-cloud bottleneck, and in this case we know, okay, each walk from C to cloud has to use W. So then the only way for this walk X to be, since it's like starts from the head of F and the tail of goes to the tail of G, is must be W. Otherwise there would be a different walk from C to cloud that doesn't use W. So therefore, since X is in the vapor, we know that our vapor now can only be one choice, that's the path. And on the other hand, if we know that the vapor is a path, then we know our walk X goes through the vapor, so there's only one choice for our walk X. And therefore, since like this is each walk from C to cloud, we know that also then each walk from C to cloud has only this one choice. Therefore, W is our C-cloud bottleneck. Okay, this is the bottleneck property, and this is what the core of the hydrostructure, so to say. Let us look at how we apply the hydrostructure in practice. So, as I said before already, for any model, if we can show that each solution walk goes from C to cloud, then we know that our walk W is safe. And this now simplifies already the single circular model, because we know that if there's an edge in the C, an edge in the cloud, then definitely we need to go from C to cloud once to connect them both with a single circular walk. On the other hand, for multi-circular, if there would be no river now, so we imagine the river to be gone, no red parts here, and we have an arbitrary amount of multi-circular walks now, so we can have one circular walk that covers the cloud and the vapor together. We can have one that covers the cloud and the vapor and the sea together. And then we have covered the whole graph. Remember, the river isn't there, without ever going from sea to cloud. So we have a counterexample. Our walk would not be safe. On the other hand, if there is a river, we remember from the connectivities, the river can only be entered from the cloud, can only be exited into the sea. So to cover the river with a circular walk, we definitely need to go from cloud to sea, and then also from sea back to cloud, because our walk is circular. So if there's a river, then in the multi-circular model, our walk W is safe. And we can iterate the same for the single and multilinear models. We can iterate the same for the subset covering models. We can iterate the same for subset visibility and for all the combinations of these models. And we always get to some useful characterization. So this is how we characterize our walks using the hydro structure, our safe walks. Let us now look at how we compute the safe walks, how the algorithms work. So first of all, simple algorithm, the verification. So we are given a walk W again, and we ask is this walk safe or not for a given model. In this case, we can construct the hydro structure in order of m time. So m is the amount of edges. And then we can, in most of the models, verify also in order of m on top of the hydro structure the characterization. So in these cases, we get order of m verification algorithms. In some cases, when we have linear model with a certain number of chromosomes, or if we have subset visibility, we get order of mn here. On the other hand, for enumeration algorithm, there's a useful property of the hydro structure. That is that we can construct it incrementally. That means we can construct it for all subwalks of a given bottleneck walk at once. And this works because if we imagine this whole walk here to be our bottleneck walk and the highlighted walk here to be our subwalk, then if we now shift this subwalk to the right along the bottleneck walk, then the sets R plus, the set R plus always increases, the set R minus always decreases. So the C always increases, the cloud always decreases. And this allows us to amortize the costs of the hydro structure computations for the different subwalks into just order of m, so into just one hydro structure computation. And then we can use this to enumerate the safe subwalks for a single given bottleneck walk in order of m plus size of the output time. And here again, we have an exception for some linear models and for subset visibility. But now we want to, of course, compute all the maximal safe walks in the graph and not just the subwalks from a single bottleneck walk. And for this one, there's another nice property that is that the safe walks in most of the models are subwalks of omnitics. And we know that omnitic enumeration takes order of mn time. And also there's another property that actually only order of n of the omnitics are bottlenecks. And so only for this order of n, we need to build the hydro structure and do this more complicated algorithm to find the safe subwalks. For the not bottleneck walks, actually, the conditions or it's very easy to verify safety or unsafety. It works in order of the length of the walk otherwise. So then we get in total a runtime of order of mn plus this order of n times order of m plus o. So we get an order of mn plus o, where O is again the size of the output. To enumerate all the maximal safe walks in any given model, except now here only for linear with a certain number of chromosomes, we get order of m squared times n. And this already concludes it. So we have now seen that with the hydro structure, we can unify the theory of safe and complete genome assembly and also solve more advanced models, as well as get optimal algorithms for most of our model combinations, except for one model combinations, as you have seen. And yeah, so we can apply it nicely. Here are my references. And then thank you very much for attending. And if you have questions, I'm happy to answer.
So please, are there any questions? Because I cannot see any questions in the chat or in the list of questions. Well, I have one curiosity. So you have clearly said that it is a theoretical framework. But do you think that the algorithms that you have described can actually be implemented, not by you actually? So I mean, or are they your theoretical interest only?
So actually, the basic onMITIC algorithm on perfect data, so on error-free reads, gives an improvement of 60% in terms of contact length and biological content. So this actually is a very significant improvement in practice. These algorithms here, I think they also can be implemented, and they probably work better hand in hand with graphs or assembly graphs that have some errors or some uncertainties, which is much more common in practice. So like, I think we can actually get some improvements in some assemblers using these kinds of algorithms.
Thanks. So I can see now one question in the chat. Does this framework lead to longer safe strings than omitics?
That's an interesting question, actually, because first of all, it leads to shorter strings because we have all these strings as subblocks of omitics. But on the other hand, now we can like take a genome graph with more uncertainties. So we don't need to delete uncertain parts of the genome graph. So we hope that in the end, we might even get longer strings using this.
Okay. Another question is, does the repeat graph, as used in the fly assembler, fit in this model?
This is also a nice question because I actually asked it to myself before, but I couldn't answer the question yet. So I would hope that it does. If it's like a genome graph and it's reasonably accurate, then I'm pretty sure that it also fits into these models, but I didn't try it out yet.
And does this model rely on read length? So can it be applied to both short and long reads?
It can technically be applied to anything where you can build a genome graph from. So if you can build from your reads a graph in which the original genome is a walk, then you can apply these models. So also from long reads. There's, for example, the assembler Watchtower, which builds a genome graph, and like this fly assembler also has a some kind of genome graph. Then we can apply this in these cases as well. Like that.
Okay. Thank you very much. Thank you very much. So chat. Okay, yes. And let's see if there are any more questions, but no more questions. So thank you again. A beautiful start to the workshop. So thank you again, Sebastian.
Thank you very much.
Next talk will be given by Bastian Cazot.
Sorry,
Yes.
Gianluca. Someone is reacting to the talk. I see some hands over the video, but I have to say that we cannot say who is reacting to the video. So if you have any question, please put in the questions or in the chat.
And I see a comment for Sebastian, a real nice concept. There is a comment on YouTube, so you're clearly not going to be able to read it from Airmeet.
Thank you very much, Sebastian.
Hi.
Hi, Sebastian. So I think it's better if you share your screen.
Yeah, yeah, okay. Normally it's work, no? Okay.
Yes, yes.
Okay. I begin? Yeah, okay. So, thanks. Okay, so I'm Bastien Cazot, and today I want to speak about the hierarchical overlap graph, and more exactly about the construction in subquadratic times. So it's a joint work that I made with Eric Rivals, which are in the Liam with me, and with Kumso Park and his student, Sungwan Park, which are in the Seoul National University. So just the outline. So at the beginning, I speak about why we want to use this hierarchical overlap graph. And after that, I speak about the main algorithm and how we can improve this algorithm by using the segment tree. Okay. So thanks, Sebastian. Just before to make me the introduction about the genome sequencing. So but just the idea is in practice, when you want to make genome sequencing and genome assembly, we need to use some type of overlap graph. So we have two big type of graph, which are overlap graph and De Bruijn graph. So Sebastian speak about De Bruijn graph, and here I speak about overlap graph. So what is overlap graph? So this is an example. So overlap graph is a weighted complete graph where the node is the set of widths that you have at the beginning, and a weight. I don't know. I think you see my mouse. So a weight, for example, here is 4 between U, this width, and V, correspond to the longest overlap. So the longest overlap. An overlap is a suffix of the first width, which are also a prefix of the second width. So here we have AACG, which are in the prefix here, and AACG is a suffix here. So it's an overlap. It's a maximal overlap here. So it's a weight in the overlap graph. But the problem that when we want, okay, I could read. So, but in theory, in assembly theory, we have a problem, a theoretical problem, which corresponds to, for a set of string P, we want to find the shortest superstring problem, which corresponds to the shortest string that contains all the string of P as substring. And we know that this problem is equivalent to finding a maximal weight Hamilton path in the overlap graph. So, for example, if we take the same example as before, so P is this set of strings, and on the left, on the top of the left, we see the superstring, and we see the string of P, which are substring of the superstring, and this superstring correspond with of the path in the overlap, which correspond to CACG. After that, we see AACGTA, and after that, GTACAA. Okay, so now if we can build the overlap graph and we find a path of maximum weight, we can obtain the shortest superstring. But one of problem is, as is a complete graph, the length of the overlap graph is quadratic in the number of widths that you have, which can be really more in practice. So to have a linear algorithm, in the last paper we presented the hierarchical overlap graph. So what is that? It's a sort of data structure. In fact, is embedded in a data structure where the node are the set of strings of the set of strings what you have at the beginning, and the maximal overlap between the strings. And for the arc, we see two different type of arc. Here it's the black and the red. The black here, we add a black arc between U and V if U is the maximal proper prefix of V in all the node. So here, for example, for AACD, the longest prefix is AA. And the red arc from U to V go from a string to the longest proper suffix. So here is CD. And this structure of suffix relation and prefix relation, we define the HOG, or hierarchical overlap graph. So this is an example. But in fact, in practice, in the last article, we don't arrive to find a linear algorithm for this graph. So we defined almost overlap graph, hierarchical overlap graph, which calls the extended hierarchical overlap graph, or EOG. And just we modify the set of nodes, and instead of taking just maximal overlap, we take all the overlap between strings. And now it's more easy to compute because you can compute it in linear time. I explain after how we can do it. But the problem that the EOG can use considerably more space than the HOG. For example, here, the node U2 is in the EOG, but not in the HOG. Okay. Why it is useful to compute the hierarchical overlap graph? The first thing is in space is less space than the overlap graph. So here I mentioned that the space of the overlap graph is the norm of P plus n squared, where n is the cardinality of P, and the norm of P corresponds to the sum of the length of the strings in P. But in fact, you can say that you can remove the norm of P because you don't need that. So it's in n squared. But the size of the HOG is on norm of P. But we can also prove that the size of the HOG is also in big O of n squared. So the size of the space of the HOG is less than the overlap graph. And also we have more information than the overlap graph because in the HOG we know if two strings or four strings, a pair of two strings, correspond to the same overlap that we don't know in the overlap graph. And also it's useful, for that is useful in shorter superstring problem, but I just mentioned that, but here it's just about the construction of the hierarchical overlap graph. Okay, so we proved before that in fact you can build the HOG, so the extended version of the hierarchical overlap graph in linear time and space in the norm of P. So this is really easy by using the Arrow-Korasik tree, for example. But in the last article, we give a norm of P plus n square algorithm in time to compute the HOG, and the space is this guy. Okay, but in fact, you can see that if all the string of P have the same length, in fact, this guys comes. It's in big O of norm de P. So where the P have strings of the same length, it's okay for the space complexity. But in the case where one string of P are bigger than the other, the space comes norm de P plus n squared, which is not really good. So here we present a different algorithm to compute the HOG, which are linear in space, but which are norm of P times log n or log n over log n in time. Okay, so to present that, I just need to define two set of overlap: the of plus, which correspond to a set of all overlap of string of P, and of P, which are just the maximal overlap between the pair of weights of P. And now, in fact, compute the HOG for us as we can compute the extended hierarchical overlap graph in norm of P. In fact, we need just to, the problem is just to how we can compute the set of the P. So the set of all the maximal overlap of P. Because if we know which node of the hierarchical overlap graph, extended hierarchical overlap graph, so EOG of P, are in of P, we can compute in linear time the HOG. Okay. So that it's just to understand how how you can compute the HOG from the Haukorastic tree, because in fact EOG, the extended hierarchical overlap graph, is embedded in the Haukorastic tree. So, for example, here, if we remove this node, which are not in the EOG because that doesn't correspond to the overlap, if we remove it and you merge the arc, you obtain the EOG. And now, if you remove, you keep only the node which are in of the P and not in of plus the P. So, for example, U2 is not a good overlap because it corresponds to the overlap between AA, BAA, which are here, and AACD with A, just A, which are not the maximal overlap because you can take AA, so we want to remove it. So, if we remove it, we obtain the HOG here. Okay. So, and in fact, it's for that we know that the number of nodes of the HOG and the EHOG, as it's embedded, the both are embedded in the Haukorastic tree, we know that the number of nodes are less than the norm of P. Okay, so now how we can build it? What is the main algorithm? So the idea here is really easy. In fact, we compute the Haukorastic tree of P. After that, we remember the string in lexicographic order. So, for example, here we have 1, 2, 3 because AABAA is lexicography smaller than AACD. Okay, so it's like that. And after that, we compute the EOG in norm of P. And after that, for each node, in fact, we can compute the interval, the EU set, which are here, which correspond to the interval of the leaf which are in the subtree when we see the black arc. So, for example, here, if I take the U1, the interval of the leaves, the interval of leaves which are in the subtree of E1 is 1, 2, 3. But for U2, it's just 1, 2, and for U5, it's just 3. And now, we will to compute of the P from the EOG. So, in fact, we need to have a good property to find which nodes are in of the P, but and which nodes are not in of the P. To understand that, we see that, in fact, what is an overlap? An overlap is if U is an overlap of SE to SJ, SI to SG, U, in fact, is a proper suffix of SG and is a proper prefix of SG. And if it's the longest overlap, we know that we don't have an overlap which are bigger. So the idea is we compute for all the leaf. We see the failure link chain. So in fact, I explain after that better, but I try to explain just before now and after that with an example. But the idea is for each leaf, we can go until the root by taking failure link chain. So in fact, we take a leaf, and after that we see the proper suffix, the proper longer suffix of this leaf, and after that you continue, and you arrive to the root. And when you make that, you see suffix after suffix, longer suffix after shorter and shorter suffix. And when you make that, you can check the interval value of the subtree of leaf and update if this pair have already seen or not. And to maintain, to store this information, we use a bit vector of length n. So the n corresponds to the number of leaf. So we have one position by leaf, and we say that BG is true if when we see this node, this element have already been seen before. Okay. So I explain in an example. Maybe it's more easy. So and we make that for each leaf. So for example, for the leaf 1. We follow the suffix link until the root. So we start from 1. After that, we go in U4, U2, and we stop in U1. So in 1, we use BG, and B the length is of size 3 because it's the number of leaves that you have. And B store, just remember that the store, if it's possible to, if we have already an overlap, a maximal overlap between from 1 to G, so to 1, to 2, or to 3. And so when you compute, for example, if we have in U4, the interval is 1 and 2. So now we can check in BG if B1 and B2 is false. If it's false, you know that A4 is the longest overlap between S1 and S1 and S1 and S2. So now you know that in the HOG you need to keep it. So you keep it, and you update the BG value for 1 and 2 to true. And you continue for U2. For U2, the interval is exactly the same, 1 and 2. But when you see in BG, these two values are already be true. So we don't need to add it. So we don't add it, and we continue to U1. And to U1, now you have 3, and 3 is false when you write. So now you need to add it, because you need to add U1 because it corresponds of maximal overlap between 1 and 3. And you continue, and you can make that for each leaf, and you obtain this this marking node. And if we remove U2, so the only internal node which are not marked, you obtain the HOG. So this is the idea. And so this is the main algorithm. So it's exactly what I presented. And if we see the algorithm, we make two different things in B. It corresponds to update. So if we have an interval, we need to update all the elements of the interval at true, and also a check. For an interval, we need to check if in the interval there exists an element which are true, which are false. So if we have these two query, so the check and the update, it's enough to make the main algorithm. And if we use just a bit vector, we can make this update thing in n, in big O of n. But now that to improve this thing, we store this bit vector B as a segment tree. So what is a segment tree? So okay, I go quick here because it's not really useful to have all the formal thing. But the idea of the segment tree, it's a tree which, for example, here it corresponds to the segment tree of the interval 1, 6. And in fact, in this tree, we can store every segment of every interval of 1, 6. For example, if I want to store 1, 5, in fact, it corresponds to this both node 1, 3 and 4, 5. And over interval. For example, if I want to see 3, 4, I need to take this node and this node. And the particular thing of this this segment tree that in fact we can update and we can update and check in log n, in big O of log n, because log n is the 8 of the tree. So by using a segment tree, okay, I pass because it's just about how it's computed in segment tree, but it's just that we know, that we need to know, it's just that, in fact, you, for each query, you only need log n. And so, as for each query, we need just only log n, and the total number of elements that you need is norm of p. It's the number of queries that we need to do. At the end, the time complexity is norm of p of log n. And as the HOG and the segment tree cost norm of p of space, the space complexity at the end is norm of p. So, so at the end, we can compute the HOG in norm of p log n time and norm of p space. But if you modify the segment tree by using the world RAM model of log n, and the world size is log n, in fact, instead of for your segment tree for a node to have just two children, you can have log n children. And now the query is in log n over log n, and now you have an algorithm in norm of p of n times log n over log n. Okay, and now just to mention it, in fact, in the open question, I had can one get a linear time algorithm? But in fact, yes, we can. With the Korean guys, we have presented in the last CPM, so it's this CPM, a linear implementation of the a linear algorithm of the HOG, and also other guys, which are Shabazz Khan, give also another algorithm to compute also the HOG in linear time, and in submit also in CPM. But the second question, which here can we extend this data structure to approximate overlaps? In fact, we don't know. I think it can be a previous question. Okay, thank you.
Thank you very much. So I'll start reading the only so far question that we have. Regarding lexicographic ordering, wouldn't it suffice to order leaves of any valid trie from left to right? The internal nodes would still correspond to an interval of the leaves.
Yeah, I don't understand exactly what's the question, but yeah, I think as it's you can ordering all the lexicographic order. You can order all the string in linear time. We make that. In fact, it's just. In fact, yes, I think we can make better, but yeah. So I think we can.
Okay, thank you very much.
You're welcome.
Are there any more questions? Okay. Just out of curiosity, any thought on the very recent preprint that proposes an optimal construction?
Okay, I just check which paper is it.
Okay,
yeah. It's one of the paper that I mentioned just at the end. It's the paper of Shabazz Khan. I think who asked the first question, and we have discussed a little both, and it's but I think we have already also an optimal construction. So yeah, so now we have two optimal constructions, so it's good.
Okay, thank you very much again.
Thank you.
So I'm introducing the next speaker,
Manuel Cáceres.
Hello.
Okay. Hi, Manuel. Please share your screen. Manuel is going to give the talk titled Safety in Multi-Assembly by Path appearing in all path covers of a DEG. Please go ahead.
Thank you. So my name is Manuel Cáceres. I am a PhD student from University of Helsinki. And today I will present you how to compute safe paths for path covers in directed acyclic graphs and applications of this to multi-assembly. This is a joint work with my supervisor, Alexandru Tomescu, and also joined with researchers and professors Brendan Moomin, Entin Husik, Romeo Risi, Massimo Cairo, and Christopher Sacchi. But first, I would like to talk about puzzles. So many problems in bioinformatics can be seen as puzzles, where we have only the pieces, and the objective is to build the entire puzzle. So, for example, in genome assembly that we have discussed here extensively until now, we have reads of some hidden genome that we don't know, and we want to reconstruct this genome from these reads. Another example is the multi-assembly, which is some sort of generalization of the assembly problem, where instead of only one sequence, we have different sequences, and we have reads mixed from all these sequences, and from this mixed set of reads, we want to reconstruct all the input genomes. So coming back to puzzles, some puzzles are solved perfectly. We can obtain the solution to this puzzle. And in general, in computer science, in theoretical computer science, we define the problems to be solvable in theory. But in practice, we see that we encounter, for example, in bioinformatics, many unsolvable puzzles. And in bioinformatics, this happens a lot because there is not only one solution that solves the problem that we are interested in, but there are many solutions. So which one we choose? So first, what we propose is, as a general framework, we're going to output only things that are for sure part of the real solution. The first thing that we could say naively is that we're going to output the input itself, because that is part of the solution, a sub-part of the solution. But we could do better also and try to output a bigger sub-part of the solution that we know for sure that will appear in the real solution. And we call to this part safe, and we want them as big as possible. So this in genome assembly are exactly what contigs are. Contigs are subsequences of the original sequence that we want to record, that for sure we know are part of the genome. And there are a lot of practical assemblers now reporting contigs. And also there is a lot of work theoretically that is not only interested in safe solutions, but only incomplete. That this is how much we can report, what is the maximum amount that we can report. And I think a good work in this topic is what Sebastian already presented for the genome assembly project. But in multi-assembly, in the other problem I presented, this is not well developed, and this is what this work is about. So the model that we are going to use for multi-assembly is a path cover in a DAG. A path cover is just a set of paths such that every vertex of the graph belongs to some of these paths. And a DAG is just a directed graph that doesn't have directed cycles. For example, this is used in RNA transcript assembly, which is some instance of this multi-assembly problem, and also in viral quasi-species assembly. And we are going to talk more about this in a moment. We developed two types of path covers. We developed two models of path covers. The first model is minimum path cover. So we consider that a solution is a path cover with minimum size. And to this size, we call it the width of the graph, because we can compute it based on the graph. And we denote it by K. And it is known that in a DAG, this minimum path cover can be computed in order B times E. But we also, for considering more practical constraints, consider a generalized version of the path covers. It is a path cover whose size is at most a parameter of the problem that we call L. And also we restrict the paths to start at and end at given input subset of vertices of the graph. So this is a generalization of minimum path cover, because we could set here L equals K and S and T equals to the whole side of vertices. So I'm going to present you our results now. We have both theoretical and practical results. In the theoretical side, we present polynomial time algorithms for computing both safe edges and maximal safe paths for both model, minimum path covers and generalized path cover, in essentially the same times for both models. So in the case of edges, we have that this work is in order K times B times E, and for maximal safe paths, in order K squared times B times E. Now recall that K is the width of the DAG. And in the practical side, we apply this framework for multi-assembly to the transcript assembly problem. And we define something that we call RNA contigs in that context. And we perform a proof of concept study in this with perfect data and also known solutions. We build splicing graph from human annotated transcript. And we found that compared to a simpler model, that our unitics or RNA contigs are double in length. We also found that the transcript coverage of the transcript is 80% by RNA contigs, and that all this for all transcript annotation runs in less than 15 seconds. So let's go now to theoretical results more in detail, and I will present this only for minimum path cover because of time constraints. So the general approach to obtain the maximal safe paths for this problem is first to compute a solution. Why we compute a solution? Because for a path to be safe, it has to be part of every solution. So in particular, it has to be part of some particular solution. So in this case, we compute a minimum path cover. We can do this, as I said, in order B times C. And then for each subpart of this solution that we have, so in this context, for every subpath of a path of the path cover, we test if this path is safe. So this is just a simple general approach. But this translates into computing the width of a reduction of this DAG based on this path that I am going to show you in a moment. Yes. So let's start with safe edges because they are simpler. So for safe edges, we have this simple theorem that says that an edge is safe for the minimum path cover problem if and only if the width of the graph changes if we subtract this edge from the graph. And the main idea here is that if we subtract an edge of the graph and the width doesn't change, it means that there is another solution that doesn't use this edge. And as such, this edge is not safe. It's not part of all solutions. So with this simple theorem, we have a naive algorithm for every path in the path cover. This is order k times b edges. We can compute the minimum path cover of this g minus e and obtain this width and compare against this. So this is the naive algorithm, but we can improve, we can do better than this. So for improving this complexity, we use a lemma in a publication of McKinnon et al. That says that if you have a path cover of size t, any path cover, not necessarily of minimum size, you can obtain a minimum path cover in time proportional to the number of edges of the graph times the difference between what you have and the optimal solution that you want. And this is based on a reduction to maximum flow. So if we do this, when we are testing one or edges for safety, we can compute the width of G minus E instead of running again the minimum path cover algorithm. You can use this, and we obtain that the complexity of every edge is the number of paths that use this edge, that we call mu sub e, times the number of edges. And if we add up all the edges in the path cover, this complexity will obtain the order k times b times e. And this is basically the algorithm for computing safe edges. For maximal safe path, we could try to do the same. Instead, we did the same, at least in the idea of what we're doing. But now it's not as simple as removing the whole path, because if you remove the whole path, you are not allowing to use subpaths of this path as part of this solution. So instead, we have to do a little more work in this case. So we define something that we call the reduction graph of G respect to the path that we are testing to be safe. And this is just the same vertices. And for the edges, we remove the last edge. And we add these edges that we call transitive edges, because these represent taking the proper suffix of the path. So here is to have a more graphic idea of what is happening. If this is the path, what we do is first we remove this last edge, and then for every incoming node to the path, we put this transitive edge that represents using this suffix of the path. And of course, we don't put the edge from the first in neighbors, the neighbors to the first vertex, because this would mean use the whole path that we would like to avoid in our test. So with this construction, we obtain an analogous theorem that is that we want to test a path if it is safe, and we know that its longer proper prefix is safe, then it holds that the path is safe if and only if, same as before, that the width doesn't change with respect to the original graph. So with this in mind, we again can compute a maximal safe path. And to do this, since we require that its longest proper prefix is safe, to be safe, then we can compute the paths in increasing size order. So first, the ones of size 2, which are safe edges, then the safe ones of size 3, 4, and so on. And with this approach, with this simple approach, and using the minimum path cover algorithm, instead of shrinking, we can obtain this time complexity. But of course, we can again use this idea of shrinking, of computing this width more efficiently, and also noting that in every path, in the first solution that we have, there are at most a linear time of maximal solutions. So we can compute them all with a 2-finger pass in that path. We obtain an algorithm that runs in order k squared times b times d. These are the theoretical results. In the practical side, we define RNA contigs. So for this, I like to recall the central dogma of molecular biology. So we have the DNA sequence here, and we have some sequences of this DNA called introns and some called exons. And these exons are, or both are important, of course, but these exons are what end up then as RNA transcript, which then become proteins. And this process from going to DNA to RNA is called transcriptions. That's what this is called, RNA transcripts. But also here, from going to DNA to the RNA transcript, it happened an event that is called alternative splicing, where exons of different parts are combined to form the different RNA transcripts. So the RNA transcript assembly problem asks to find the RNA transcript of a sample. This is the objective. And the input we have are reads, but not reads from the DNA, but reads from the transcript. So from the reads from the transcript, we want to obtain the transcript itself. So one known technique, which is genome-guided technique, is first to map these reads to the DNA or this pre-RNA if you want. So in this way, you can identify which are the exons that are part of your sample of transcript. And you can also identify that some of these reads align to maybe 2 exons. And this means that these 2 exons in some transcript are together in that transcript, are consecutive, I mean. And with this information, you could build the splicing graph, which is just a representation of this information where each vertex represents an exon and each edge represents some of these double mappings that we have in 2 exons. And this is a DAG. And naturally, by its definition, a solution to the RNA transcript assembly problem is a collection of paths in this graph that it is a path cover of the graph. So if we go back to our definition of generalized path cover, we could use or L. Remember that we are interested in paths of size at most L to be 3, because in this case there are 3 transcripts. We also know where these transcripts start and where this transcript ends. And this can be, for example, in this case, identified by either upwards or downwards slopes in the mappings of the exon when we do this mapping here. So we can obtain those. So with this information, we have a generalized path cover. We model in this sense. We define the RNA contigs as the maximal safe path for this generalized path cover. So now I will tell you a little about what we did as an experiment. And we worked with human gene annotation with all the transcript information from chromosome 1 to 22 on the forward strand. This means that we already know the answer. So we have the transcript which are the position of these transcripts in the genome, and we also know what are the corresponding exons. So in a sense, we know the answer. That is why this is a perfect scenario, because we don't consider errors, and we already know the answer. And to experiment, since in practice we don't know the number of transcripts in our sample, or maybe we don't know them, we test L to be the minimum possible paths, the width of the DAG, until 2K, 2x the minimum number. As a baseline comparison, we take ST unitics, which are just an extension of unitics. These paths in the graph whose internal nodes have in degree and out degree equal to 1. Because those are safe in the problem, because we have to cover vertices. So our results. The first result is that the algorithm runs in less than 15 seconds. And then we have this table here that tells about precision and relative maximum coverage. So in terms of precision, we know that for T and 2K, T is the real number of transcripts. We are 100% precise, which is what we expected because we are computing safe paths. But when we are not considering the real number of transcripts as part of the input, we see some loss in precision here. We can also see here the relative maximum coverage is how much of a transcript we cover with one of these contigs. And we can see that it is up to 80% in small graphs. And it's always better than Unitix. And in fact, this comparison between Unitix and contigs, it is shown here. So in general, we are 1.4 to almost 2 times longer than ST Unitix. So to end this presentation, I would like to make some conclusions. So we present some efficient algorithms that obtain all maximal safe paths for generalized path coverage for this definition that we have. We did a proof of concept of RNA contigs on human annotated transcript. Everything, the code, the dataset, and the manipulation script are available in this URL. And we also consider that future development of safe paths in generalized path coverage is possible and it is worth. So for example, apply to other multi-assembly problems, not only RNA transcript assembly. It can be used also to validate current assemblies, and it can be used as a pre-processing step of the real assemblers, or just as contigs are used as simple as output of the multi-assembly problem. So that's my presentation.
Thank you very much. And I'm inviting people to ask questions. I have one in the chat. You mentioned alternative splicing. I guess you include other RNA maturation events, such as alternative start, termination, or transcription.
I'm not aware of what this means, but the nearest that I can relate to is parameters S and T that we have, that we consider to give us as input of our algorithm a set where we know that the transcript starts giving the information we have according to the reads and where the transcripts end. I don't know the technical concepts, the names for.
So I think that I'm trying to interpret that question. That is, what are the alternative splicing events that you have considered in your experiments?
Alternative splicing.
Well, what kind of events do you have?
Only the events that one transcript can be formed from different subsets of exons. That's what we consider.
So there is no restriction on the set of events?
No other than that.
Okay. Then from YouTube, if I understand well, you presented a graph resolution method. What is the expected quality of the input graph in terms of real depth, technology, assembly method?
Okay. I have to read something to answer that. But I know that current assemblers have precision that is really low in terms. I think it was less than 50% of precision of current assemblers. Between 50 and 60%, sorry, of precision of current assemblers. But of course, these assemblers lead with real data issues as errors and
yes. So I think that the question asks for what happens if the input graph is noisy.
I think the resulting the result will be different because we only tested in imperfect scenario. But I'm not sure how it will behave. We haven't tested that.
No, that's fine. Another question is how would the use of long reads affect the approach?
Okay, that's a good question. Because here, if you notice, here, our model considers only path cover as a model. So we only require the path, the transcript, to cover all the vertices, all the exons in that case of this graph. But we don't consider long reads. And long reads would mean to have subpath constraints. That is to require to the path cover that a subpath of the graph exists in the path cover. And we are at the moment working on that. So I don't have a definitive answer for that question. But it's a really good research question.
Yes. Thank you very much. And these are I really appreciate your talk. So if there are no more questions, we are going to have a break. We are resuming the talk at 3:30. So that is in 50 minutes. Clearly, you are invited to join the tables and to chat with some of the other participants. So see you again in something less than 15 minutes. Bye. Bye for now.